in the last lecture we were looking into the control hazard its associated problems. We had seen that for MIPS 32 instruction set architecture, the pipeline implementation, we can reduce the branch penalty to one cycle, because we mentioned that at the end of the ID stage we can know both the outcome of a branch, whether it is taken or not taken branch, and also the branch target address. So, in the worst case we have to incur a penalty of one cycle. So, you should say that well, one cycle is fine. For load followed by use we have one cycle, here also one cycle. So, let us see, but you see one thing, let us make a simple calculation. So, we saw in the earlier example we took in the last lecture that the ideal CPI was 1, 30% of branch, but here we are saying that branch penalty is one cycle. So, what will be the actual CPI in that case? The actual CPI will be 70% of the case when there is no branch, CPI will be 1, the ideal, and for the 30% of the cases there will be one cycle penalty. So, CPI will be 1 plus 1, 2. So, it will be 0.7 plus 0.6, 1.3. So, you see still you have a 30% degradation. This is still quite substantial, right. Let us see how we can reduce this further. So, this is the topic of our discussion in this lecture, how to tackle the hazards, in particular the control hazards further. Let us see. So, our specific target here will be to reduce the pipeline branch penalties. So, we start by discussing 4 broad techniques. First is a very naive approach. We have seen that a branch will incur one cycle penalty. So, whenever there is a branch, you freeze the pipeline, insert one stall cycle. This is the simplest approach. Main advantage is simplicity, but as I had shown in that example just now, that the overhead can be significantly high still. So, with the figures in the example I took, we saw that there can be 30% performance overhead. Now, the other approaches are based on some kind of prediction. Second approach says we predict that the branch is not taken, and we allow the hardware to continue as if the branch is not executed at all. That means, the next instruction is fetched, it is executed, and we continue as if nothing has happened until the branch outcome is actually known to us. So, when the branch outcome is actually known to us, then we can know whether our prediction was right or wrong. If we see that our prediction was right, we do not do anything. The next instruction which was already entered into the pipe, which was already executing, let it continue and execute. We do not incur any stall cycle for that, but only if we find that our decision was wrong, it was actually a taken branch, we are assuming not taken, then we will have to stop that, insert a stall and fetch the new instruction from the target. Okay. So, let us take an example. So, if it is a not taken branch, then there will be no penalty, that means it is a branch instruction, but the branch is not taken. So, the sequentially following instruction will be executing after that. So, the hardware will be assuming that the branch is not taken. So, it will fetch the consecutive instruction without any stall. So, for such cases there will be no penalty, but if the branch is actually taken, then at the end of the ID stage you will come to know that your prediction was wrong, because it is here you come to know that your branch is taken or not taken by decoding the registers, right. So, if it is wrong, then there will be one stall cycle inserted, and for this case you will be incurring a one cycle penalty. But for some of the cases there will be no penalty, for some cases there will be one cycle penalty. Okay. The third approach is we predict that the branch is taken, just the reverse. we assume that the branch is always taken. But unfortunately for MIPS 32 you will see that this prediction does not help, because if we predict that the branch is taken, that means you will always be fetching the next instruction from the target address, and the target address is known only at the end of ID, right. So, only after ID you can start the fetch. So, anyway this one cycle will get lost. So, irrespective of whether it is taken or not taken branch, for MIPS 32 this one cycle penalty will always be there. So, here the idea is that whenever the branch outcome is decoded and the address is known, that means at the end of ID, fetching of instructions can continue from the target, that means here. So, as I said, for MIPS 32 we know the branch outcome and the target address both together. So, there is no advantage in this approach, because in both cases there is one cycle penalty. For more complex instruction machines, maybe this will help. So, where possibly the branch address is known earlier, but whether it is a taken or non-taken branch, that is known much later in the instruction execution cycle. For those kind of complex instructions, maybe this predictive strategy will work better, but not for MIPS. This really does not work for MIPS. Okay. All right. And the last approach is called something called delayed branch. Delayed branch, what it says that, well, there is a branch instruction, let that branch execute. It can be a taken branch or not taken branch. Now, the assumption is that the slots which are following that branch instruction, where you are normally inserting the stall cycles. For MIPS there was one stall cycle, I said, okay, for branch. So, there is one stall cycle, we call it as a branch delay slot. What we are saying, that the instruction which is there in the delay slot, that means one instruction will be fetched after the branch. The assumption is that that instruction will always be executed, and the compiler knows that, irrespective of the branch is taken or not taken. So, the compiler will try to put some instruction in the delay slot which is supposed to be executed every time the branch is executed, irrespective of it is a taken or non taken. Okay. This is the basic idea. So, this is called delayed branch. Here we are making the hardware simple, but we are putting all the responsibility on the compiler. So, in general a branch instruction can have n stall penalties, but for MIPS 32 we have said that it is only 1, n equal to 1, but in general I am showing n. After this n penalty, the next target address will be known. So, the next instruction can be fetched after that. Okay. So, these n successor instructions are called branch delay slots. For MIPS it is 1. Okay. So, the compiler will try to move instructions around and try to fill them up, and as I said, the interpretation is that whenever instructions are put in the branch delay slots, in this strategy, in the fourth strategy, these instructions are always executed irrespective of the outcome of the branch, whether you take it or do not take it, right. Fine. So, let us take some examples. Suppose I have an add instruction followed by a branch, if R2 is 0, jump to L, and there is a delay slot after that. So, you see the add instruction is executed before branch always, right. So, there is no harm if I move this add to the delay slot, because whenever there is a branch, the delay slot will also be executed and the add is coming here. So, we are saving this time, we are not wasting the delay slot, rather we are moving a useful instruction. So, whenever the branch is taking or not taking, add will always be executed. This is one example. The other example is a little complex, something like this. Suppose I am adding, I am subtracting, getting a result in R3, and if R3 is 0, we are jumping to L. After that, there is a delay slot, but the add instruction does not depend on R3, it is independent of R3. So, here we move this this add instruction to the delay slot. So, we subtract, we do a branch, then we jump. While we do a jump, during that time the add is executing, right. So, this is just a responsibility of the compiler to just compiler will be analyzing the code and find out if it can move some instructions like this. Similarly, another scenario, there is a add, then there is a branch to L, there is a delay slot after branch, and after that there is a subtract instruction. The subtract instruction you can also use R3, does not matter because branch outcome is already done. So, this subtract can move to the delay slot in this case. You see, in the second and third cases, during the last iteration, maybe this instruction you are moving, that will be executed one extra time. So, the compiler can analyze the code and find out if that one extra time execution will actually matter or not matter in the final computation of the result. If it does not matter, it can safely move it, and if it is possible to move an instruction, that means you are avoiding that one cycle stall due to control hazard. You are moving a meaningful instruction in the delay slot, and when a branch is executed, the instruction in the delay slot is also executed. Okay. But this is done only for pipeline implementation where this strategy is followed, but for other strategies you will have to insert that stall. Okay. Fine. So, for delayed branches there are some other difficulties, like you will be having some multiple program counters, because in fact it will be n plus 1. So, means other than the target address, so all the instruction in the delay slot also need to be restarted if there is an interrupt in between, right. So, there are multiple values of the program counter that need to be saved, because the PC of the branch target and the PC of the delay slot, they are not sequential. Branch you are doing somewhere else, and PC delay slots are the instructions right after the branch, right. Okay. Let us take an example. Let us consider pipeline with an ideal CPI of 1. Let us say 20% of the instruction are branch, and out of them 70% are taken and the remaining 25% are not taken. So, using the 4 strategies we discussed, let us evaluate the speed up. So, speed up we will be calculating using this formula, this ideal CPI multiplied by pipeline depth divided by ideal CPI plus stall cycles per instruction. This we have derived earlier already, because ideal CPI is 1, we put 1, and pipeline stall cycle per instruction in this case will be branch frequency multiplied by branch penalty. So, we will be using this formula. So, let us look at the 4 possibilities. The stall pipeline strategy, where you are stalling always, your branch penalty will be 1. So, you just 20% of the instruction are branch and 75% are taken. So, for all the branch you are stalling. So, for 0.2 branch penalty will be 1. So, 0.2 multiplied by 1, if you calculate, speed up becomes 4.17. The second strategy, predict not taken. So, you will be incurring the overhead only for the 75% of the cases where the branch is actually taken, right. So, you speed up is higher than this, you see 4.35, but predict taken here means you are incurring the penalty again all the time, because there is no advantage, it is same as stall pipeline. And for the last strategy, delay slot, delayed branch, here for the branch you are trying to move an instruction in the delay slot. I am assuming that there is 50% probability that the compiler will be able to fill up the delay slot. So, I am multiplying this by 0.5. So, if you calculate, you will see that you get a higher figure 4.55. Okay. Fine. Now, interrupts pose a more difficult problem in a pipeline. Let us see in the MIPS 5-stage pipeline, integer pipeline, whenever interrupt comes, what are the issues? Interrupts can complicate the design of the pipeline. How? See, overlapping of the instruction execution makes it difficult to decide whether an instruction can modify something. When I say safely change the state, it means either it changes the value of some register or something. See, suppose an instruction changes the value of a register, later on it is found that there is an interrupt, that instruction has to be withdrawn, but already it has modified a register. What to do that? That is a problem. Okay? So, the instruction should not change the state of the machine before it is known that the interrupt has occurred or not. Some interrupts can force the machine to stop the instruction before it is completed, like the page fault interrupt. So, whenever you are trying to fetch an instruction where the memory location from here fetching is not there in memory, it has to be fetched from disk. That is the example of a page fault. Okay. So, under those cases, the instruction has to be restarted after the requested memory contents are brought into memory from disk to memory. You will again execute that instruction, you will be restarting it. Okay. So, such interrupts are more difficult. So, the most difficult interrupts have the properties that they occur in between an instruction and they have to be restarted. These are the more difficult types. So, one strategy for interrupt handling can be like this. So, whenever an interrupt occurs, this interrupt can occur in any stage. Okay? It can occur in IF, ID, EX. So, a special trap instruction or some kind of a flag is forced into the pipeline at the next instruction fetch cycle, which will indicate that an interrupt has occurred. And until this, see, the control unit will know that this trap instruction was inserted, and the control unit will not allow any writes to occur. It will disable all writes, not only for the instruction which generated the exception or the interrupt, but for all the instructions which follow it. And this will continue until the trap reaches the WB stage. Until the trap comes out of the pipe, you will be disabling all writes, and when the trap comes out, then only the interrupt handler or the interrupt service routine will be activated. It will save the program counter of the instruction that generated the page fault, and it will process the interrupt. Now, for delayed branches, it is a difficult condition that I had said, that the instruction in the branch delay slot might have caused the interrupt. There was an instruction which is present in the delay slot that can cause the interrupt. So, if the branch is taken, so what I mean to say is that there was a branch, let us say a branch equal some target label, and there was a branch delay slot, let us say there was one delay slot. There are some instructions here, let us say XYZ, and this instruction XYZ has generated an interrupt. So, in the pipeline, this branch instruction was already there, it was fetched, it was, let us say, decoded, it was executed, it was supposed to do mem and WB, and the next instruction is supposed to also execute along with it. So, XYZ should also be supposed to be fetched here, decoded here, executed here, and so on. So, what I am saying is that suppose this instruction during the EX stage generates an interrupt. So, you will have to stop everything, not only this, but also this branch instruction, you cannot jump to the level. So, you will have to stop everything, and when you come back, you will have to not only restart this XYZ, but also the instruction that is there in this target label, some other instruction, let us say an add instruction is there, also this instruction. So, multiple program counter values have to be saved, the PC of this XYZ and also the PC of this, right. This is what is mentioned here. The instructions to restart are those in the slot plus the instruction at the branch target, which requires or needs a number of PC values to be saved and of course restored. So, actually when the interrupt is handled, after that there is a special instruction in MIPS 32 called return for exception RFE, that is the instruction to be given at the end or the last instruction of the interrupt service routine or handler, that will be reloading the PCs automatically and restarting the interrupted instructions. So, for these kind of delayed branch kind of machines, the RFE instruction had to do a lot. It will have to reload multiple PCs. So, there is a terminology called precise interrupts. Precise interrupt says that let us say an interrupt has occurred. So, if it is possible for the control unit to stop the pipeline such that all instructions before the instruction that generated the interrupt can complete and all instructions that follow will wait, they will be restarted later, then we say it is a precise interrupt. Okay. So, as if you see the definition, if the pipeline can be stopped such that the instruction before the faulting instruction are completed, while those after can be restarted from scratch, then we say it is a precise interrupt. Well, there are cases, let us say for page faults and also for IEEE arithmetic, this precise interrupt is a necessity. So, the designers of these pipelines, they spend some effort to ensure that interrupt handling is precise. And just a quick snapshot. So, what are the kinds of interrupts that can generate in the 5 stages, the exceptions? In the instruction fetch stage, there can be page fault while fetching the instruction. There can be misaligned memory access, because we said that all instruction fetches have to be from a multiple of 4, memory address should be a multiple of 4, but by mistake if you have given a misaligned address, that will also generate an exception. Okay. And memory protection violation, you are trying to access from a memory location where you do not have the access rights, access permissions. For ID you can get illegal opcode, for EX you can get let us say divide by 0, some kind of arithmetic exception. Mem same, page fault, misaligned access, memory protection violation, and WB there is nothing. Multiple interrupts may occur in the same cycle, this is one danger. Like here let us say a load instruction followed by an add. Here load instruction can generate a page fault during mem, while this add can generate an arithmetic exception during EX. So, 2 interrupts are being generated in the same clock cycle. So, one solution is that if this kind of a thing happen, so you ignore the second instruction interrupt, you only handle the first one and again restart. So, if the second instruction had generated an interrupt, it will generate it again. We deal only with the page fault and restart the execution, the second interrupt will occur again and will be handled at that time. Okay. This is one solution you can think of. The second difficulty is that interrupts may appear out of order. Let us take another example. The first load instruction may be having a page fault here in mem, and this add instruction can have a page fault in IF. So, it is out of order. So, for out of order interrupts, that means the earlier instruction is generating interrupt later, later instruction is generating interrupt earlier. So, a possible solution to this we will be just discussing briefly. The solution is like this. the hardware will post each interrupt in a status vector. Like you see, you have the pipeline stages, right. You have the instruction fetch, you have the instruction decode, you have the execute, you have the mem, you have the WB. So, what we are saying is that when the instructions move from one stage to the next, there is also a special register value, a status register, which is part of the interstage latches. This will also move from one stage to the next, right. This is the status. This will move like this. So, what we are saying is that this status vector is carried along with instruction as it moves to the pipe, and in that status vector you set a bit indicating that there is an interrupt and also the type of the interrupt. So, you do not do anything here, you let it move, and when it reaches WB, only then you process the interrupt. Maybe the interrupt has occurred here, but you allow it to move till WB. When it reaches here, you see that what is the type of the interrupt. You see it was an instruction page fault, then you handle that interrupt, right. So, when the instruction reaches WB, the interrupt status vector is checked and handled. But if you do it like this, then preciseness of the interrupt is guaranteed, because the first instruction will be reaching WB earlier, the following instruction will be reaching WB later. So, the first one to reach will be the earlier instruction. So, maybe the instructions were generated out of order, but the first instruction will always reach WB earlier than the next instruction. Okay. So, the interrupt for the first instruction will reach WB earlier. This is the idea, right. So, this is what we mentioned here, that interrupt handling will be carried out in precise order, and with this we come to the end of this lecture. Now, in the next lecture we shall be discussing some more methods to improve the control hazard handling.